You guys should all be familiar with the structure of the atom. But for those monkeys who aren't really sure, here is a short summary. This is a good-looking carbon-12 atom. This means it has 6 protons and 6 neutrons. I am not going to elaborate, so if you don't understand, blame yourself for being an ape. Anyway, here is carbon-14. Carbon-14 has 6 protons, 8 neutrons and 6 electrons. Both are isotopes, and carbon-14 is unstable while carbon-12 is not. Carbon-14 will try their best to stabilize itself through radioactive decay. Contrary to popular belief, radioactive decay might not actually be random. But since igcse students have smooth brains that are incapable of comprehending the sexy concepts involving complex atomic physics, we are just going to move on. Anyway, if the nucleus has too few neutrons, it would emit a package of 2 protons and 2 neutrons called an alpha particle. It is also a helium-4 nucleus. This process is called alpha decay, and it causes the mass number to decrease by 4 and atomic number by 2. It has a positive charge of, as you might have guessed, 2. If the nucleus has too many electrons, a neutron will magically transition into a proton and emit a fast-moving electron. This electron is called a beta particle, and the process is known as beta radiation. A beta particle has a relative mass of 0, so its mass number is also 0. To summarize, a beta particle is basically an electron. Beta decay basically increases the atomic number by 1. It doesn't really do anything to the mass number. It has a charge of -1. Now let us get to the fun part. After emitting an alpha or beta particle, the nucleus will often remain hot. This would cause it to lose energy by emitting an electromagnetic wave. High-energy particles will emit energy as they drop to lower energy levels. They will emit an energetic electromagnetic wave called gamma ray. Because gamma ray is basically energy being released, it doesn't affect the atomic or mass number. Now let us talk about the different properties of nuclear radiations. We will first compare their penetration power. Laugh. Alpha particles could penetrate skin or paper, and it can travel up to 5 centimeters. It's very good at ionizing stuff, which means it's really good at adding or removing electrons. Beta particles can penetrate aluminium foil, but it's not very good at ionization. It can travel up to a meter or so. Gamma rays are insane, just cracked. Gamma rays can penetrate pretty much anything in its way, even the surface lead or concrete, and to be safe from it, you either have to be kilometers away or hide behind a thick wall made of concrete or lead. It's really bad at ionizing. In space, these bad boys can travel very far, because they will never stop. Now let's talk about how those bad boys behave when they are being affected by electric and magnetic fields. Look at this figure. Alpha particles head to the negatively charged region because they have a charge of +2. Oh, they also have a relative mass of 4 atomic mass units, or 4 AMU. Beta particles head there, for you should know why. Their relative atomic mass is 1/2000 AMU, and they have a relative charge of -1. They have a large relative deflection, as you can see. The Chad gamma rays are as straight as my sexuality. It has no relative atomic mass, nor does it have any relative charge. It is unaffected. Literal Sigma male. So cool. Are we done? No. We are going to talk about background radiation. You are always exposed to background radiation. Yeah, it sucks. Background radiation could be due to cosmic rays, radioactive rocks from the Earth, or radioactive decay taking place near you. Because there are so many factors, background radiation is pretty much random. You can also detect radiation using a cool Geiger-Müller tube. This contains argon gas, which is poggers. The poor argon gas would constantly be attacked and ionized by radiation, causing electrical pulses to be sent to the radiometer. There are other ways to measure or detect radiation, such as photographic film, gold leaf electroscopes and more, but they are kinda shit, and most of the people use the convenient Geiger-Müller tube, or a Geiger counter. Same thing. Are we done now? No. Let us talk about half-life, baby. not the game. Half-life is basically the time taken for the number of unstable nuclei of a particular isotope to have. It doesn't matter how many atoms you start with. After one half-life, half the atoms will decay. It will reduce by 50% after one half-life basically. It has pretty simple. Okay. Goodbye. Simple. Okay.